We now move back to our example about the possible effects that smoking have on pulmonary function as measured by forced mid-expiratory flow. And we're going to run an Anova test with alpha equal 0.05 for the provided data. Okay, so we had 6 groups. If you go back and you look at the data, there were 5 groups of size 200 and 1 group of size 50 for a total of 1,050 observations. We want to find the average, the overall grand mean for those observations. So that's a weighted average of the sample means. So that's going to be 200 observations for the non-smoking group times 3.78 plus another 200 observations for the passive the passive smoking group with a mean of 3.30 plus 50 observations for the non-inhaling group, which had an average of 3.32, plus 200 observations for the light smoking group, which had a mean of 3.23, plus 200 observations for the moderate smoking group, which had a mean of 2.73, and then plus 200 observations for the heavy smoking group, which had an average of 2.59. So we're going to add all that up and then divide by the total number of observations, which was 1050, which gives us a grand mean of 3.135. Now, if I had access to the individual observations, I could have added all of the FEF measurements for those observations and then divided by 1050, but I only had the sample means to work with and sample sizes in this case. I want to find the sum of squares treatments. That's going to be the sum from I equals 1 to 6 of n sub I y sub I bar squared minus ny bar squared. You'll notice I'm using lowercase letters here because I'm working with the data now. I'm not working with the random variables that represent the data. Okay, this is going to be 200 times 3.78 squared plus 200 times 3.30 squared plus 50 times 3.32 plus 200 times 3.23 squared plus 200 times 2.73 squared plus 200 times 2.59 squared, and then I need to subtract ny bar squared, so that's going to be 1,050 times 3.135 squared. When I do that, I get a total of 184.376. That's the sum of squares treatments. I'm also going to need the sum of squares of the air. That's the sum from I equals 1 to 6 of n sub I minus 1 times s sub I squared. So in the first case, there are 199 for the degrees of freedom. And for the non-smokers, we had a standard deviation of 0.78, which we'll square. Then we had the passive smokers and the standard deviation of 0.77, which we will square. I'm going to fix really quickly that that's actually supposed to be 0.79 squared for the first standard deviation. The non-inhaling group had 50 observations for degrees of freedom of 49 and 0.86 squared for the variance there, plus 199 for the light smoking group with a standard deviation of 0.78, which I'll square, 199 for the moderate smokers, 0.81 for the standard deviation squared, and then 199 of the heavy smokers, 0.82 for the standard deviation squared, for a total sum of squares error of 663.866. And now I want to summarize all of this data in my Anova table. Okay, so the degrees of freedom treatments is 5. The sum of squares we saw is 184.376. So when I divide by the degrees of freedom, 5, I get 36.875. The degrees of freedom for the errors is 1,044. The sum of squares was 663.866. And the mean square we saw when we divide 663 by 1044 is going to be 0.636. Okay, the degrees of freedom total is 1049. That's n minus 1. And then the sum of squares total, I'm going to add the two sum of squares. So that's 848.243. The F statistic in this case is going to be the mean squared treatments divided by the mean square error. So 36.875 divided by 6, or 0.636, gives me 57.99, which seems quite large. So I'm expecting to have a small p-value. So what I'm going to do is I'm going to go look at the F distribution chart, but I'm going to show you a different F distribution chart, and that F distribution chart is one from a different book. I think it's a little bit easier to read in this scenario. Okay, so degrees of freedom for the numerator are on the top of each page, and then the denominator's degrees of freedom kind of go down the column. So that was degrees of freedom 1, and here it is 2, 3, 4, and then finally degrees of freedom 5. Okay, we're going to look at an alpha level of 0.05, and if we look down, we're going to want to look at degrees of freedom somewhere between 140 and infinity, because we have 1,044 for our denominator degrees of freedom. Okay, so that means our cutoff is in this column. It's somewhere between 2.21 and 2.28 if we're going back and looking at our alpha being 0.05. So 57 is much greater than that. Let's get a sense of the p-value. Well, it seems to be off the chart. It's bigger than the values that are there. So if I go back up, I can see my p-value has got to be less than 0.0001. So I will make this F chart available to you. I find this one is a little bit easier to use in these circumstances because it's specifically designed for ANOVA, because the degrees of freedom for this chart in the numerator doesn't go beyond, say, 8 or 9 groups. Okay, let's go back to our computation. So our p-value we know is less than 0.0001, very highly significant. I plugged it in to R and I got 2 times 10 to the minus 53. So again, very highly significant. So we're going to reject our null hypothesis. Okay, that means that smoking has some sort of effect on mean pulmonary function. Okay, so we can conclude the mean FEF for at least one of the groups is different from the others. Well, that's good. Now we know that smoking does have an effect on pulmonary function, but which one? Which groups are different? Is one group different from the others? Are all the groups different from each other? Which ones are statistically different from the others? Well, you'll have to watch the next lecture to find out about how we can distinguish the groups. So I want to conclude with, when can we use this Anova test? Okay, so this is a test where we would normally want to do a t-test, but we have multiple groups. Those groups must be independent. The observations within those groups must be random samples. The group population distributions must be approximately normal. Okay, so we either have to have a large number of observations or the underlying distributions are going to have to be normal. And then finally, and this one's going to be the one that's a little bit different, is group standard deviations must be approximately equal. So you'll see we used the group standard deviations earlier in our computation. We saw that they ranged between 0.77 and 0.86, so they were all approximately equal for this study, and we need that to be true in order for us to be able to apply that F distribution like we had done, or like I showed you in the previous video. So group standard deviations must be approximately equal. Well, that finishes an example of how to apply ANOVA, and so now we want to move on to finding out which ones of the different groups might actually be statistically different from each other.